Welcome to the Space Telescope Public Lecture Series. Tonight's presentation, The Vibrant Life in Cities of Galaxies by Mireia Montes of the Space Telescope Science Institute. I'm your host, Dr. Frank Summers of the Office of Public Outreach here at STSCI. I want to thank our amazing tech team, Thomas Marufu and Grant Justice, who are doing this recording and streaming it live to YouTube. We also remind you that our Space Telescope Public Lecture Series will remain online only until further notice. Our upcoming lectures in February, we have From the Front Lines of the Exoplanet Revolution. Our Peter Roy, also of the Space Telescope Science Institute, will be talking about planets around other stars. And really, it is a revolution that has happened over the last 25 years. In March, Hubble from Space, an integral field spectroscopy from the ground, seeing both the forests and the trees. A great talk title, I'm sure he's going to follow through it, that shows the advantages of space-based observation as well as the advantages of ground-based observation and how they work together. That's Mark Sarzi from the ARMA Observatory and Planetarium. And in April, a really cool talk for you, Neutrino Astronomy with IceCube. Had you ever think you could do astronomy using neutrinos? Do you even know what neutrinos are? Well, pay attention because Marco Santander from the University of Alabama will be talking about that in April. To keep up with all of our talks, you can go to our website, www.stsci.edu/public-lectures. And this is the web page that you will find. On the left-hand side, you can see our webcasts, both on our YouTube playlist, as well as our STSCI webcast archive. And on the right is that wonderful little box where you can enter your email address and subscribe to our lecture announcements, and you'll get 2, maybe 3 emails a month. Also on our website, we have a list of all the upcoming lectures. And if you click on each lecture for more information, you find the description, the speaker, as well as after it's been recorded, the link to the STSCI webcast, as well as the YouTube webcast. To sign up for our email, well, as I already said, sign up at the website. But if you don't want to have email, if you want to use it by YouTube, you can subscribe to our YouTube channel, youtube.com/Hubble Space Telescope. That's all one word, Hubble Space Telescope. And as a subscriber, you will get notices of new videos, as well as reminders of live events. Finally, if you have comments or questions, you can send them to our email address, publiclecture@stsci.edu. You can also reach us via social media. We have social media channels for the Hubble Space Telescope, for the Webb Space Telescope, and for our institute, the Space Telescope Science Institute. So Facebook, Twitter, YouTube, and Instagram available there. I myself do a tiny bit of social media. You can find me on Facebook and Twitter as Dr. Frank Summers. And now our news from the universe for January 2022. And this is a special presentation because really there's only one story to tell you right now, okay? This is what's really consuming our time. The James Webb Space Telescope has launched, okay? And if you were here last month, you heard all about the James Webb Space Telescope. So I don't need to tell you too much. I just want to remind you what it looks like. This is the Webb Space Telescope in its fully deployed configuration. But it's not quite there yet. We've been waiting a really long time for it. And I wanted to just give you a feeling for just how anticipated this launch was. So the timeline of selected events, that's just, I cribbed from Wikipedia, right? 1996. What was then called the Next Generation Space Telescope was initiated. Now, actually, the first discussion started in about 1994. That's a symposium to say, all right, what are we going to do after Hubble? Hubble is, was working and doing great stuff, but what are we going to do next? So in the mid-1990s is when all that started. And then in 2002, it got renamed to the James Webb Space Telescope. In 2003, the prime contract was awarded. So we're talking, 18 years ago when the prime contract just started for this telescope. It takes a while to do all this stuff. The mission critical design review passed in 2010. And then a really crazy thing happened in 2011. Something happened in a congressional staffer's office. They zeroed out the JWST budget, right? And it was threatened with cancellation, but we survived that. That was quite a tense summer here at the STSCI in 2011. And then we'll look towards launch, but that starts in about 2015, where the contract for the launcher with a launch date of October 2018. And we all really were focused on October 2018. Meanwhile, they completed the JWST construction on all the instruments and all the mirrors and everything, and they started into the serious testing phase. And testing is extremely important for this telescope because unlike Hubble, we can't go up and repair it, okay? So it's a really complex telescope, and we got to get it right the first time. So testing is absolutely crucial. And that's what we found out that it needed further testing. So in March of 2018, it got delayed to May 2020. And then in June of 2018, it got delayed a little bit further to March 2021 on the recommendation of an independent review board that really wanted to make sure everything was going to go right. Okay, so then you get the pandemic happening, okay? And in July 2020, we had to postpone it again because of the pandemic impact, as well as some technical challenges. So that became Halloween of 2021. That was our target date. And then in June, they had some problems with the Ariane 5. And they said, well, due to things we got to test out and make sure everything's going to go great with the launch rocket. So it pushed it back to November. And then in September, the launch got postponed a little bit more and a set date of December 18th. We're going to go mid-December. Okay. And then there was additional testing that was required. And again, you got to get the testing, you got to get it right. So no earlier than December 22nd. And then there was an electrical fault that said, okay, no earlier than December 24th. And finally, one of the things you always expect at launches is that there was weather. And so that pushed it to December 25th. And then on December 25th, from Kourou in French Guiana, this is the spaceport with the Ariane 5 rocket. We got to watch exactly on time. We got to watch this.
And liftoff. Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
So astronomers got their holiday present. Here's one of the shots that was posted to our Slack channels. Amazing stuff. We were just so excited. We were following it. It was 7:20 in the morning on Christmas Day. And this shot captures a very special moment because the rocket puts it up, and then at some point the telescope separates from the rocket. This captures it 27 minutes in. And of course, that is just a visualization of it, okay? Because we don't have a camera flying along with it to track it. But on the top stage of the rocket, there was a webcam. And a few minutes later, about 15, 20 minutes later, they actually got the footage from that separation. All right, so this footage from the separation is actually kind of rough because it's real data, okay? And there's blips all through it. It's not clean. And the one other thing to look out for is at the very end, the extension out of the sun shield, not the solar array, because Webb is a solar powered telescope. So the first thing it needs to do is get power from the sun. So this was really cool to watch. This is just very stirring to those of us at ST.
James Webb Space Telescope, amidst applause here in the Mission Control Center, now taking its first steps in pursuit of cosmological discovery.
Yeah, that was quite the moment. So, JWST is going out to its orbit at around the second Lagrangian point, okay, which is a semi-stable point. And usually we show you a diagram like this. But look in the lower right corner, it says the diagram is not to scale. So I thought I would show you a diagram that actually is to scale. And so this is one of the possible orbits, okay? Actually, the orbit does depend upon the launch date. So the exact orbit, this isn't the exact orbit, but it's an example, a good example of it. And you can see that it's not going out to the L2 point and sitting at the L2 point, okay? It's a semi-stable, gravitational semi-stable point, and instead it's orbiting around that L2 point, okay? It's a very large orbit, okay? The size of that orbit is the diameter of that orbit is almost the same size as the distance from Earth. So it's a really, really big halo orbit around it. And this is what allows it to maintain that position. And we can use a minimum amount of fuel for station keeping to keep it in that orbit. So along the way out to the orbit, it will be doing its deployment. As you saw last month from Alex, at the origami telescope has to open up and the sun shields stretch out and so on and so forth to get out there. It takes about 29 days to get to the L2 and insertion into the L2 orbit. And so you may ask, well, where is Webb now and what stage is it at? Well, to find that out, you go to a very helpful website that's called Where is Webb? Hey, and this was a screenshot I took from Where is Webb this morning. And at that point, layers 1, 2, and 3 of the sun shield layer tensioning had been completed. And about 2 hours later, about noon Eastern time today, the sun shield deployment was complete. Yes, that was a point that we have really been waiting for, okay? Because you got 5 layers of sun shield, you got to pull it out of the booms and everything, just really complex stuff, and it's working beautifully. In NASA speak, both the launch and the deployment are nominal, which in NASA speak really means it's going perfectly. It's really going well. So we are so excited about this. However, we're only 10 days into the mission. And as I said, on day 29 will be the orbit insertion on L2. So if you want to follow it, if you want ongoing information about Webb, I'll give you 3 web URLs. You might want to screenshot this so you can refer to them later. First is this Where is Webb site, which gives you a lot more information than what I showed in that one screenshot. It has a bunch of other screens where you can really go through all the stages of its deployment and a lot more information about Webb. The official NASA Webb blog has articles, short articles written as each thing completes. They tell you exactly what's going on. It's fantastic. And then when there are particularly interesting things going on, the NASA Live will cut in. Like today between 9:30 and noon, they covered the sun shield tensioning, okay? The separation of the layers and tensioning of the sun shield. They covered it live. And it really was, it was fantastic live reality TV because, it really means something. This is the deployment of the NASA's next great observatory. So these are the 3 places that I've been following. I invite you to follow them. And we got a wonderful holiday gift for astronomy. And next month, I'll hopefully be able to tell you that it's at LL2 and everything's going great. So let's get back to our main talk tonight. It is Mireia Montes talking about the vibrant life in cities of galaxies. And Mireia is an STSCI fellow here at the Space Telescope Science Institute. And she works in the Wide Field Camera 3 group. So Wide Field Camera 3 is an instrument on the Hubble Space Telescope. She got her PhD in the Canary Islands at the Instituto Astrofísica de Canarias. I'm sure I butchered the pronunciation of that, but I did my best. She did a couple of postdocs, one at Yale, up in Connecticut, and another at the University of New South Wales in Australia. So she has been quite the world traveler. She also has her own hobbies where she does a specific type of belly dancing that I don't know anything about, so you'll have to ask her about it. But she has both a great spirit and a great outlook on life. And so, ladies and gentlemen, very proud to present Mireia Montes.
Thank you very much, Frank, and thank you very much for this nice introduction. Hello, everybody. It's a pleasure to be here. It's a pleasure to share with you my passion and my knowledge with you all. So let's start with it. As an astronomer, my job is looking up at the sky. So, well, maybe Baltimore is not the best place to look at the sky. So let's go somewhere else, somewhere darker, and where we can see like some stars at least. So as Frank mentioned before, I lived in Australia for 3 years before coming to Baltimore. There I got the opportunity to observe here this is the Anglo-Australian telescope inside the Spring Observatory that it's located almost 7-hour drive north from Sydney, where I was living. So the first night I was there, there was a problem with the instrument that we were using. So although the night was the most perfect night that you can imagine, it was clear, there were no clouds, it was just perfect, but we were not able to observe anything. So what we did is we went outside, and this is the first time that I saw what you can see here in this image. So this is this lane of bright and dark patches, that is our Milky Way, and also the satellites of the Milky Way that are the Magellanic Clouds. And you can see one of them here. So those satellites can only be seen from the southern hemisphere. So I was really, really excited. So one fun fact that I want to tell you before like going on with my presentation is that while in the Western Hemisphere we define constellations as the groups of stars, Aboriginal Australians look at these dark patches that you can see here and saw the shape of an emu. An emu is like a large bird that they have in Australia. So it is like that. And once you see it, you're never gonna not see it again. So this emu, and they call it the emu in the sky. So at a particular point of the year, the legs of this emu in the sky will disappear below the horizon. And that will signal Aboriginal Australians that it was time to, like hunt to look for the emu eggs. That was part of their diet. So this is by far one of the most clever uses of astronomy I have ever heard. Well, that and like basically like developing technology to have like Wi-Fi and other things. But let's go back to the sky. So this lane of dust and stars is our Milky Way. So because we are inside the Milky Way, we can only see one part of it. So it's very difficult to know how it actually looks like. So one of the things that we can do like sort of like a little play here. It's like if we look like close to this lane, we can see more stars than if we look like like far from this lane. So basically, this is telling us that our galaxy has like some some sort of flat structure, like kind of a pancake. And actually, this is what astronomers do. Like, so basically, they count stars. They count the stars. They know where they are. They calculate the distance to figure out the shape of our galaxy. So, for example, this is a map of the Milky Way by astronomer William Herschel in 1785. So basically, he did that. He looked at the stars. He estimated some sort of distance, and he put them on a map. So yeah, basically what he saw is the same thing, is that our galaxy is some sort of like a flat disky structure. Well, in Herschel's map, we see that we are located here. This is this very dark, like darker point. So he thought that we were located like some sort of in the center of our galaxy. But fast forward to today, with better instrumentation and precision, we know that the Milky Way looks similar to this, from the top. It's a spiral galaxy. We see here, like the spiral arms. We are sort of like in double in between arm. And our galaxy has this very like fuzzy blob of orange blob of stars in the center, this elongated shape. And we are not in the center of our galaxy, but we are kind of like halfway out. So, so we know that if we observe the universe, we know that there are more galaxies, and all these galaxies come in very different shapes. So there are galaxies that look like this one, like a fuzzy blob of stars that have like a roundish elliptical shape. That is what we call elliptical galaxies. Their color is like this gold, yellow, orange. That indicates that the stars in these galaxies are old, and they are pretty much not forming stars. These galaxies were formed very long ago in very intense, like very short and intense episodes of a star formation. So kind of they form in like at once, all the stars in these galaxies. The most massive galaxies in the universe are typically of this shape, elliptical galaxies. Next, we have spiral galaxies like our own Milky Way. They can have more or less defined spiral arms. Sometimes, like the center, it's more or less dominant, and sometimes they have like this kind of bar-like structure in the middle. These galaxies are bluer because they contain more, like more of younger stars. So in this case, like compared with the elliptical galaxies, the star formation has occurred like longer in time, more constant over time. And finally, we have galaxies with like not a particular shape, and that's what we call irregular galaxies. So in comparison, these galaxies are less massive than the other two types, and their stars are young, and they have less metals. So they are bluer, and because they are less massive, they tend to be like a satellite of the other two types. So in the same way that the stars in our Milky Way, they were not distributed evenly all over the sky, galaxies are not distributed evenly all over the universe, but they, like us, they like to live in communities. So when we are talking about, like dozens of galaxies, like some sort of like a town, maybe that was too much, very, very low populated here. We are talking about a group of galaxies. For example, our Milky Way, our own Milky Way, lives in a rather small group that consists of Andromeda, which is our nearest spiral galaxy, our galaxy, the Milky Way, and their satellites. If we are talking about hundreds or even thousands of galaxies, more like a, like a proper city, we are talking about clusters of galaxies. These are some of the biggest structures in the universe, and they are like, well, of course, for me, they are very interesting. But let's look at them and what they can tell us. So this cluster is Abel 1689. It's a favorite of mine. What you can see here, so let's look at this image. So what can you see in this cluster? What is the most striking feature that you can see in here? So we see that most of the galaxies in the image look like those elliptical galaxies. They look like yellow, orange, like, you know, these fuzzy blobs. So compared to other places in the sky, we can see a higher number of these orange galaxies. We can also see that, you know, like we have some big galaxies over here, over here, over here, but there are like these tiny galaxies, and you can see that there are way more. So in clusters, while, you know, like while tiny galaxies dominate in number, there are more tiny galaxies. Most of the stars are in these, you know, like in these big galaxies. So basically they dominate in light, so they dominate in the brightness of the cluster. So if we look at the cluster itself, we also see different parts. There is a higher concentration, a higher number of galaxies in the center of the cluster, a higher density, which is like the center of a city. However, if we move like away from the center, we go to the, you know, like the outer parts, there are less number of galaxies, which is kind of like the suburbs of a city, you know, like basically the galaxies there have more space, which is, you know, like what happens if you go to the suburbs, you have more space. So in the center of a city, because of the highest density of people, you're gonna basically see more people, you're gonna experience more interactions, you're gonna talk to people, you're gonna, you know, experience more encounters with other people. That is the same that happens with galaxies in the center of the cluster. Well, apart from the, you know, like they don't talk, they interact they interact with each other, but in another way. In this case, the interaction that they experience is a gravitational interaction. So when two galaxies, you know, like pass by, you know, like they come very close, the you know, like the difference of like this difference of gravity. Think about like, you know, like you have like a chalk and you're like writing in a blackboard. So when you're writing, you're liberating this kind of dust. That is what it's basically is basically the word that you have there. So it's kind of the same with stars in galaxies. So when they come together, the stars of these galaxies, they are stripped of their hosts, and basically this interaction is kind of slowly breaking these galaxies. So in the very center, there's normally a big galaxy, and the stars from the other galaxies that are around, they become deposited in that galaxy, in the big galaxy, and in its surroundings, making this galaxy grow over time. So, you know, like an example, this is our nearest cluster. This is the Virgo cluster. As you can see here, there are like these ridges of stars, these tails of stars, and the space between the galaxies and the cluster, it's not empty, it's filled with all these the stars that were stripped from this host galaxy while they are kind of interacting with this bigger galaxy. This is M87. So basically, this big galaxy at the center behaves like a kind of like a hungry monster that will not stop eating till, you know, it devorates all the cookies, or in this case, it devorates all the galaxies that are around. So So another thing that we observe in these clusters is that, like the center, most of the galaxies are yellow, this yellow-orange, but the galaxies, when we look at the outer parts, the suburbs, the galaxies are on average a little bit more, they're not that yellow. They are like a little bit more, bluer. So there's like a mix of colors of galaxies in these outer parts. So these outer parts are very, very interesting because this is the boundary between, like the cluster, these higher density regions of the cluster, and the rest of the space. So this is where the galaxies that are being eaten by the cluster travel to get to the center, and this is where they experience this change. So one of the most astonishing examples of this, of this process is, this type of galaxies. You can see the galaxy here, and you can see these tails of these very blue tails that are very, very young stars. Those are called jellyfish galaxies because they actually, look like jellyfish. So while, like in the interactions in the center, you can see, like you can see what is happening. You see which is the culprit that is destroying the galaxies while they interact. In this case, there's nothing around that can tell us, oh, that is creating this and that will change like the shape of this galaxy. And this is because we are not looking where we should be looking. So the images that we normally see, it's in the optical wavelengths, is the wavelengths that our eyes can see. But this is like a really, really tiny part of the electromagnetic spectrum. Let's see what happens if we change our glasses and we look in another part of this spectrum. If we look in, for example, in X-rays. So this is our cluster, Abell 1689, and this is in the visible. This is the like what we can see. We can see the stars, the galaxies. But this is how it looks when we see it in X-rays. It looks really, really different. So what is happening here? What is this? So galaxy clusters are filled with large quantities of gas that is really, really hot. It's so hot that it emits in X-rays. And it's the interaction with this hot gas that is causing the tails of the star formation in the jellyfish galaxy, the galaxy that we've seen before. So it's kind of having like an underground party scene in the city. So you hear the music, but you cannot actually see the people dancing. Well, okay, I understand that this analogy might be a little bit forced, but like I hope that you can forgive me this one, and you can kind of understand what I'm saying here. So galaxies have gas, which is, in this case, is cold gas, which is the fuel to form stars. When they enter the cluster, they are welcomed by this hot gas of the cluster. So imagine like, like when you turn around a corner and there's like this strong wind that, like just like hits in your face, it messes your hair, like it just gives you your hair, like, like back and messes your hair, and probably this is not in your hair. So this is what is happening to this galaxy. So it's basically, it's traveling through space, it hits this gas, and it has knots, in this case, knots of star formation. So that's the jellyfish galaxy that we saw before. And in this case, this blue light over here is what we see in X-rays. So these X-rays are basically the gas that is being removed from the galaxy while it's forming, making these new stars. So, and that is why the galaxies in the inner parts look redder. There is not a lot of star formation going on because the there's not a star formation going on in the inner parts of the clusters, because this hot gas is very good at removing most of the fuel that forms the stars in galaxies. So although this gas is not very dense, it is very important in clusters of galaxies. In fact, most of the mass in clusters is in this gas. And I say mass, quote unquote, because there's something else in clusters of galaxies. Okay, let's go back a little bit back in time to 1933. So in 1933, this guy, Fritz Zwicky, you know, with the nice picture, was measuring the velocities of the galaxies in this cluster, the Coma cluster. So he was measuring the, he was measuring the velocities of the stars, and he found that those velocities were too high for the cluster to remain like a cluster. So with the observed velocities, the galaxies would have escaped if the mass that is in there, it's the mass that we see, the mass in stars. And that is what he wrote in his original paper. He wrote this. And if you know, like you have like the same level of German that I do, which is basically 0, you might appreciate that I include the translation. And here there are two things that I want to emphasize, so I want to highlight. This is first is this word nebel, that is the German word for nebula. So in 1933, we were still calling galaxies nebula, which is, it's not very important, but like I find it funny and I wanted to share this with you. And the second thing is this, the dark matter. So what he found is that for the cluster to be together, to be like a cluster, there should be more matter than what we see. So basically, to explain why the cluster is together, it is necessary to have like around like 100 times more dark matter than mass in stars. But wait, haven't I told you that there's like this hot gas, and that like it's like there's more mass in this hot gas than mass in stars? Yes, that is correct. But it is the gas is only 10 times the mass in stars. It still cannot account for all this other mass that we need. So we need something else, and this something else is what we call dark matter. So the stars, the gas, and basically us is what we call normal. It's basically normal matter, which is what we call baryonic matter. But dark matter is not baryonic matter. We don't know what it is, but we know that it's not our like this normal matter that we are made of. So the problem here is that we don't know what it is, and dark matter does not emit, so we cannot observe. The only way that we know that it's there is by how the things that emit, the galaxies, behave. For example, in this case, it was the velocity of the galaxies that indicate that there was more mass in the cluster than like what we could see. But there are other ways to to kind of see this dark matter. Another way is what we call gravitational lensing. So if you have a huge mass, the gravitational field that is created by this huge mass distorts and magnifies the light from the galaxies that are I don't have anything, you have like this mass, and it distorts and magnifies the light from the galaxies that are behind the cluster. So we are here, somewhere here. And basically, this this huge amount of mass, which is our cluster, it allows us to see things that are behind, which we could have not seen if there was not this effect happening. So basically, those the clusters are acting as telescopes for our telescopes. So we can see and explore the far universe. So when you look at an image of a cluster like this one, you see all these arcs, here, 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 here. This image is amazing. You have all the arcs that you can imagine. This is the cluster Abel 370. It's one of the frontier fields clusters, if you want to know. So those arcs, these things, are not part of the cluster. They are behind the cluster. So, and the only way that we could see it is by this effect, the gravitational lensing. So what gravitational lensing does is telling us how the matter distributes in clusters. So again, we have our favorite cluster, Abel 1689. And let's pretend that we can have like a way of seeing this matter. And this is how it looks in, like this blue, purple light. It's how the matter of the cluster, it's how the total matter of the cluster distributes. So, and you can see here that it's very different of the, like how the hot gas was distributed. So galaxy clusters and like this technique, the gravitational lensing, has provided the strongest evidence for the existence of this mysterious dark matter thing. And the evidence is given by this cluster, which is the bullet cluster. So there are actually two clusters that have collided. This is not the kind of collision that you would imagine. This is, like it's a cosmic collision. This is very different. So in this image, you can see the blue is where most of the mass is, that is given by the gravitational lensing. And the pink is the hot gas, is basically the cluster in X-rays. So and you can see here, these are the galaxies of the two clusters, and you can see that they were not affected by the collision. They just went like passing through. But the gas has been affected by the collision. Instead of like being here where the galaxy is, it has being like kind of left behind. So that is telling us that, like that there's more mass than what we can see, because if the only mass in the cluster was the stars or the galaxies and the gas, the galaxies, instead of being over here, they will have followed the gas, because it's where most of the mass is, and it's what, like it just creates this gravitational potential. That is where, like galaxies like to be. But instead, in here, you have that most of the mass is over here in this blue part, and over here in this blue part. So this is telling us that there's something else, that we have more mass, and this mass is what we call dark matter. So we have all the pieces together to form our cluster of galaxies. We have the hot gas, we have the galaxies, and we have the dark matter, which I painted it in blue so you can actually see something. The gas accounts for like 9% of the total mass of the cluster, while the galaxies, the stars and the galaxies, account for like around like less, sometimes less, and around like 1% of the total mass of the cluster. But the dark matter, which is the component that dominates, it's 90% of the total mass of the cluster. So it's a lot of dark matter in there. And what are the masses that we are talking about? So we are talking about like 10 to the 14, 10 to the 15 solar masses, which is basically 10 to the 14, 10 to the 15 suns, which is basically a one followed by 15 zeros. And I'm not sure if you can imagine that, but I certainly cannot. And if it helps, it should be like around like 1,000 Milky Ways. I'm not sure if that helps, but just in case. So with that mass, with this very, very high mass, and the fact that we've seen that they are held together by, by gravity, makes galaxy clusters the largest structures in the universe that are held together by gravity. And this is very important because there are structures that are larger, but they are not linked, they are not held together by the gravitational potential. So they are kind of less interesting. Just kidding. They are less interesting for me. So how do you form these structures? So by observing the past and the present, how they looked in the past and how they look now, we can deduce how they form. In the same way that you build a Lego toy by, like tiny bricks, putting together tiny bricks, clusters grow by adding small systems. In this case, galaxies or groups of galaxies. So I'm going to show you now a simulation that's an example of how this process, how we think that this process it's happening. And you can see like there are like these two clusters, and they will come together, they will merge, they will create like a very big cluster. And also you will see that the galaxies, how the galaxies in the cluster they interact. And they interact, they lose the stars, and the stars ends up forming like a big galaxy and like a big cluster in general. So let's a little bit here. This is what we think that will happen at the end stage of a cluster, having like this very big galaxy sitting in the center and this very basically huge clusters. This is the illustrious TNG50 simulation, just in case you want to know. So the first stages of these clusters is basically kind of like a baby cluster. Is what we call protoclusters, although I think that I like more baby clusters. These protoclusters hold important clues about the details of the growth of these structures. As you can see here, this is one example of a protocluster that is being observed, and you can see here that it doesn't look like at all like the clusters that I've shown you before. They just there are like random galaxies all over the place, but I can assure you that this is a protocluster. So while we have had success finding these protoclusters with our new and now shiny JWST, it will be possible to discover more of them. So with more clusters, our knowledge will be much better of what is happening in this in the formation of clusters. And James Webb, it's especially suited to discover these things because they are they are high redshift, they are very far away. The light basically they are emitting in the infrared wavelengths. So James Webb, being a telescope that observes in the infrared, it's just the best telescope that we can imagine for this. So we are looking forward to have the first images of this telescope and be able to discover more and more baby clusters. So what I wanted to leave you is with the idea that galaxy clusters are some of the, well, for me is the most fascinating objects in the universe, but I know that my friends will shout at me. So there are some of the most fascinating objects in the universe. And from them, they're formed by stars, by gas, and by dark matter. We can learn a lot from them. We can learn a lot about gravity, about dark matter, and about normal matter. So yeah, they are the best things in the universe. So thank you very much. Please ask any question.
All right. Thank you very much, Mireia. That was a nice exploration of these really large entities in the universe that, I guess since most people just recognize that we are in the Milky Way galaxy, if they recognize we're in a galaxy, they really don't, they don't get much exposure to these giant clusters out there, do they?
I mean, we have like, like these very nice images that, like the ones that I show, that they're like really, really striking, right? They're very fascinating when you see the images, but I don't think that we know a lot about the science that it's going on in them. I think that they're, like the science, the things that we can learn from them are such, like this fascinating, basically.
Right. So one of the questions that people have is, our Milky Way, is it part of a big city? Is it part of the suburbs? Is it out in this remote village on the edge of nowhere? What's the Milky Way status here?
So we would, I don't know, like if I have like the perfect analogy for our Milky Way, because our Milky Way lives in a group of galaxies, but it's like a very, very, like it's very small group. It's a they call it poor group. So it's basically the Milky Way, the Andromeda galaxy, which is another big spiral galaxy, and it's just satellites. So there's not a lot of galaxies in this small group.
Okay, so our Milky Way is like a town or something like that, or something.
Yeah, it's like maybe in a very tiny town.
Maybe a village. All right. So how far away is the big city from us? I mean, if we're how far, are we really country bumpkins? And how far do we have to travel to get to the big city? In galactic terms?
We are talking about billions of light years. So don't think that we can get into the city.
But I guess we would consider Virgo as sort of like the nearest big city.
Yes, Virgo is the nearest big city, and still Virgo, it's not like a huge city. It's kind of like I don't know, the smallest city. There are clusters out there, like the one that I've been showing. Those galaxy clusters are, I don't know, Mexico, New York, Mexico DF, Sydney. There are
the biggest cities we've got, right?
Huge cities.
Yeah, the frontier fields clusters are always the frontier fields clusters. Those are the biggest ones, the ones that produce gravitational lensing. Whereas, like Virgo, you're saying that might be like a Baltimore or something like that. Yeah, not quite as big. Okay, great. All right. Well, we had a lively chat here. We've been following it, and I wanted to bring on Grant Justice, who's also been following it, to pull up some questions. So, Grant, if you come on, say hi to everybody, Grant. Hello. And what questions did you find that were interesting?
Sure. Like you said, we had a really good chat tonight, and starting off kind of from the beginning, chronologically, so it'll make a little more sense. One of the first ones was in some of your earlier illustrations, the dust that was being drawn towards the galaxies. Was that gravity creating that, like the trail being drawn in, or was there some other force acting upon it?
I think you're talking about the jellyfish, the stuff that's actually being drawn out. All right, so I think maybe the people might have confused that as stuff being drawn in versus being drawn out. Why don't you explain that again, Mireia?
So the jellyfish galaxies is what I said. It's kind of like it encounters like this kind of wind. So basically, all the gas. Imagine that you have like, I don't know, like you have glitter, and there's like, I don't know, like my analogies are like really, really bad. I'm sorry. You have glitter and there's a lot of wind. So, like all the glitter or whatever you're, it's just, like being dispersed like behind you, right? So this is what happens with the cold gas that are in these galaxies. So they are, they are like blown away. The gas is blown away from the galaxy, just it's being removed away from the galaxy. And in that process is because it's being disturbed and it's being, like just everywhere, and it's forming these clumps of star formation, these new stars.
So these galaxies are actually orbiting through the cluster. They're
Yes.
moving through the cluster, and then this stuff is being pulled out as it's moving through. Okay,
Exactly. Yes.
I think
So basically,
yeah.
Basically, what they have found is that these tails of the jellyfish is telling us how the galaxy is moving through space, right? Because
Yep.
you know, like it's going there, and the tails are behind you.
Okay, great.
And what is it that causes the wind? Like, where's it coming from?
So that is a very interesting question, and because we don't know exactly. So there's this hot gas that has been, you know, like being accreted. So you bring all the galaxies inside, and you bring all the gas too. So you know, like the thing is that you have all this gas that it's, you know, like floating around, and the particles of the gas will collide, and at some point it will kind of cool down. But what we've seen is that it's not cooling down. So there's something like some energy that it's just making it still being hot. We still don't know what exactly. It might be like, you know, like merges between clusters that it just like excites the gas. It might be like AGNs that basically inject a lot of energy into this gas. We are still not sure exactly which is the mechanism that is just, you know, like just moving the gas.
Right, because you're heating this gas up to X-ray temperatures where it emits X-rays. So that's really hot. So
that's that's a lot of energy.
That's a lot of energy to come in. All right, so there's a related question to that. So one was trying to just get a handle on that. There are stars in these clusters that are not part of any galaxy. And how much of that? How many of these are there? Is there any way to quantify that?
Yes, that's actually those. I don't know who was that person, but that person probably knows what I work on. This is, you know, like those stars. There are stars in those classes that they do not belong to any particular galaxy. They just float around, and that is called what we call intra-cluster light. And this is actually what I work on. Like this is my actual expertise is on this very diffuse, very faint light in classes of galaxies. So this is the thing is that we because it is so faint, it's very difficult to separate between the galaxies and this faint light because we only have images. So it's kind of difficult to quantify exactly. There are estimates that around 20% of the mass in the stars are in these stars that are not that they do not belong to any galaxy. They just float around.
Okay, so about 20%.
Like around 20% of the stellar mass.
Stellar mass, right? Yes.
Yes.
That's actually, as an astronomer, that's actually surprising to me. I wouldn't have expected it to be that large. So, obviously, I need to read some of your papers, don't I?
Sure. Yes, I'm actually I've been asked by Nature Astronomy to write a review on intracluster light, so you know, like I can send that to you.
Okay, great.
That actually leads well into the next question, which is the chat has been talking quite a bit about this, as I'm sure you can imagine. What would be your suggested like reading for someone who's a little bit more interested in your talk here today, and especially regarding like the quantity of dark matter, regular matter, and these sort of like interacting forces?
I'm not sure because, you know, like what I'm used to read all the time is, you know, scientific papers. So I'm not sure about any specific, more like outreach side, you know, like less slang, less jargon, and more, you know, like plain language. I would maybe suggest if you can look into, there's a book of a collaborator of mine that is called Priya Natarajan. She's an expert on you know, like all things dark matter, and she has a book that is called Mapping the Heavens. So maybe you can look into this.
I'm going to put
I'm
it
sure
in the
that
chat.
she's.
Chat,
Yeah.
I'll put it in for you.
I will say that Priya actually gave a talk here in the public lecture series a couple years ago. So, all right, great.
Awesome.
Let's see what else we got here.
Okay.
Actually, I want to go into the X-ray because everyone was massively amazed that coma looked so, or 1689 looked so bland in X-rays, and one of our viewers speculated, well, maybe the X-ray resolution is just really, really, really bad, and they can't see the individual galaxies. And they wanted they suggested that as a reason why the X-ray looks so bad. Doesn't have any detail.
So if you look back to that image and you can Google it, like 1689 X-rays, you can see that there's like the big blob, and there are like two small blobs that actually there are like two galaxies. So yeah, the resolution in X-ray is it's a little bit less good than in the visible light. Also because like we are comparing anything with Hubble, and Hubble is like basically the best resolution that you can get now. Well, wait a month or so, and
we'll take it while we can get it.
Yeah,
it counts. It counts. It counts.
I mean, like I like Hubble. It's my favorite telescope. So so it's already a little bit unfair that we are comparing like things with Hubble images. But yes, the resolution of an X-rays is worse, but it cannot explain, like this basically big blob there in when we see clusters of galaxies.
Yeah, and you also showed the bullet cluster, which shows that the X-rays do have good resolution in the bullet cluster.
Yeah,
right. It just means that I think it just means that 1689 is so hot and so massive that it's just it seems like it's just one blob.
Yes,
because there's just so much there.
and it's one blob.
It's one blob, but
it's the gas that it's just emitting.
A lot of things also appeared as one blob in the past before we got the fine instrumentation and control to discern the blob.
But I'm saying at 1689, it could discern it if the substructure was there. I think the telescope could have discerned it in 1689. All right, what else you got, Grant?
All right. Okay, so what do you think will be the end of these large-scale galactic structures?
So we see something that is called fossil groups. That basically it's like like this huge, massive galaxy in the center, and then you have like like this not that massive like satellites around. So it seems like what we want, what the clusters want, is to be like that, right? Having like this very massive central galaxy, and maybe like a few satellites that they have still not managed to merge into the central galaxy. So basically that it seems like it's what it wants it to be. It's like it's what the gravity is telling it to be, right? Just being like kind of not boring, but yeah, kind of less structure than what we see now.
Also boring on a galactic scale. I feel like that needs air quotes.
I mean, like
that's not really boring.
Like the X-rays are boring too, but it's still it's hot gas that emits an X-ray, which
it's mind blowing, but while it's still being boring, right?
Like it's hard for explosions to be boring. I'm just saying.
Yes. All right. So somebody asked this one. I actually asked it a couple times. In other galaxies. All right. So you went through the components that are in supposedly our galaxy, right? Mm-hmm. Do we see other components not beyond the dark matter and the stars and the gas in other galaxies? Do they have other components that we don't have in our galaxy?
No. They're like like basically these parts that are forming. So you can have the gas, cold gas, warm gas, hot gas. You have like all these phases of the gas that are like just going around. But basically, well, another thing that I have mentioned, but you have seen it in when we've seen like basically the lane of the Milky Way is dust. That is basically some molecules that are kind of not cold, but like they are very opaque, and they basically obstruct the light. So that's why we cannot see the center of our galaxy, because there's all this dust that is in front of us.
Right. Okay,
I remember
so
that being the
other galaxies basically have the same components, but maybe in different proportions or something like that. But nothing new in the universe that we don't see nearby.
Well, I mean, I think that with dark matter, we have plenty of like weird things too.
There's plenty of weird things out there. Okay, Grant, what you got?
All right, so let's see what we got. Reading through some of the further comments as we've been going through the questions here.
Yeah, they do this to us. It's just like we're trying to answer and look at the camera, right? Then we have to look down.
Yeah, I feel bad looking away. All right, so all right. Well, here we go. Entropy increasing. All right, this isn't a bad one. If entropy increases, won't we end up as like eventually a homologous solution? Do we intend to like see the black holes make their way throughout? Like we just kind of spoke about it a little bit with the death of like supermassive structures, but on a slightly more galactic scale, like where do you see this going?
With entropy, that is that is very outside what I know.
This is the problem we run into. We have such lovely fields.
But it's a natural question. All right, so we build these bigger and bigger clusters of galaxies. What's the end? What's the long-term fate of the universe? Yeah.
I mean, like
logical.
What we know is that it seems like there's this thing that is dark energy, which if we don't know what is dark matter, we don't know like anything about dark energy, which is like basically pulling apart. And they were saying that it would be like this, call it big rip.
The big rip,
like kind of, it's like kind of the, like just everything would be dismantled, like just
right. The acceleration of the expansion of the universe will continue to accelerate until everything just rips apart.
Yeah.
I don't find that satisfying as an ending.
It's kind of like it's
kind of an intergalactic anticlimactic zipper. Like
it's like
guess we're done now. Okay, I could see it. Ultimately unsatisfying. I agree.
There was a really good question about the bullet cluster.
Oh, please.
Somebody noted the bullet cluster that the dark matter was separated, and they said, "Well, wouldn't that dark matter want to be together?"
So yes, that is the thing. Is that like you have those clusters and they collided, which is basically the pass-through. But the thing is that it's kind of like the first passage. So they will, because of the gravity, they will like kind of like tend to do this like pendulum thing until they basically are together.
Right. And matter of fact, the observations of the bullet cluster are so intriguing because it's a non-equilibrium situation, right? It hasn't relaxed.
Yes, because like once we don't see the effects of this. Well, one is like like a little bit far out of this collision state. The gas will tend to go through like to the kind of gravitational potentials of the two.
Okay, so we have a perfect last question for you. Okay. How do you study the diffuse emission from the intracluster gas? Somebody who listened to what their previous question. Is this something that JWST will help you with?
So so what I do is not the gas. I do the stars, which is
the
intracluster
light, yes.
to see. So yes. There's a lot of things in the question because I study because the observations that I need are so deep that there are very few clusters that have been observed. So there are still, clusters nearby that we haven't been able to explore. And also we want to know like what happened to this light, in clusters like, like a redshift 1 or, like when they were like more younger. So we want to see the evolution. That is in the past is where Webb will help me to study this diffuse light.
Oh, fantastic. Do you have programs to study these distant clusters with Webb yet?
Not yet.
Not yet. Okay. Well, we won't get the first observations, even just the early release observations, until this summer. So, we got some time before we'll be able to get the cluster observations.
There are surveys that are being made, with these early, observations. So maybe there's a cluster over there that I can, study. So,
as our resident dust expert, Dr. Lawton, would like to say, it's JWST is his savior for all of the dust. So hopefully we'll get some more advanced and through imagery for you.
All right. Well, I think we've told the audience just about everything you wanted to know about galaxy clusters and more. Although I'm sure there's still plenty more to tell. Thank you very much, Mireia. Next month, February 1st, from the front lines of the exoplanet revolution, presentation by Arpita Roy. Join us then. Thank you for joining us now. Take care.
Thank you, everyone.